Hello students, welcome back. We completed section 1 along with the optional topic of types of errors. Now let's go to section 2, hypothesis testing for population means 1. Now what's the difference between section 2 and section 4? In section 2, we're going to confine ourselves to the problems that require only the z-distribution. Here's a checklist that we considered earlier. From simple random sampling, if we have large sample, typically 100 or more, then you can apply the central limit theorem, so normal approximation works. So we use z-table. Small sample, 50 or less usually, then depending upon whether the original population is normally distributed or not. If yes, then we have second criterion, known sigma or unknown sigma. We use either z-distribution or t-distribution. If not normally distributed, then tough luck. You have to go back to the survey design or sample design to begin with and then take larger sample and start over. This kind of thing you won't have to worry about at all as far as you're taking exams or doing homeworks or things like that in class. Outside class, it's important. Here's another version of it based upon the textbook. Okay, here's a problem. The drying time of a type of paint under specified test conditions is known to be normally distributed with a mean value of 75 minutes and a standard deviation of 9 minutes. Wait a minute, haven't we seen this before? Well, actually, it's the very same problem as this. We went through all that, and here is the conclusion, so let me just copy and paste it. So set up appropriate hypothesis, okay, null and alternative hypothesis, and here are appropriate numbers. Sample size of 25, straightforward. Sample mean of 72.3, again, that's pretty straightforward. And we are taking the significance level of 0.02, again, is specified. What is not that simple is to find out whether this 9.0 is a population standard deviation or a sample standard deviation. I think I used blue for population standard deviation before, so let's stick to that. Here, the problem only mentioned the standard deviation of 9 minutes. Is it really population standard deviation or sample standard deviation? It did not tell. In fact, no problem will explicitly tell you that, except for extremely simple. Extremely simple problems may tell you, but in practice, no problem will actually tell you that. You have to figure it out. So how do you figure it out? This information came along with a null. Read the problem again. Known to be normally distributed with the mean of 75 minutes and the standard deviation of 9 minutes. This information came along with a null. It did not come with a sample. Null means no, none, nothing, zero, empty. You didn't do anything and you still have this. This came out of nowhere. It did not come from the sample, okay? Normally distributed with a mean value of 75 and a standard deviation of 9 minutes. They all point toward this normal distribution has mean of 75 and a population standard deviation of 9 minutes. So it's sigma we are talking about. Now how about the sample part? It's coming from here. The mean drying time of 72.3 minutes in 25 observation. And if this has cut and pasted to this red sentence here, then with the same phrase, you have to say this is a sample standard deviation. Let me copy and paste that here. And the mean Okay, if the problem had been written like this, then this is pointing toward the sample standard deviation. See the difference here. Original problem versus, let me put some space in between. The original problem versus a variation. Pay attention to the colored part. I did not specify in the problem whether the standard deviation given is population standard deviation or the sample standard deviation. I just placed it in the right place. Normally distributed with a mean value of 75 minutes and a standard deviation of 9 minutes. It came with a null, not from the sample. So this is sigma. Now go down here. I changed the problem a little bit. Normally distributed with a mean of 75 minutes. Stop. And then let's go to the next sentence here. In a lab test, the researchers obtained the mean drying time of 72.3 minutes and the standard deviation of 9.0 minutes in 25 observations. So the standard deviation came with a sample. This problem did not specify sample standard deviation of 9 minutes. It just says standard deviation 9.0 minutes, but it was placed along with a sample. Here, not specified as population standard deviation, but it was placed along with a null. See the difference? Often tricky, but it's an important point, especially if you're interested in scoring high in an exam, because in an exam environment, it may be a bit mean, but there are all kind of things there. And the context problem is certainly one of them. So, in short, we have population standard deviation, and the original population is normally distributed. So what are we using? Even though the sample size is just 25, less than 50, we use the normal distribution, the z distribution with the z-curve and the z-table. Make sense? Okay, all right. One down, about 4 or 5 more to go. Oh my goodness. Getting the decision making, that was a big step. Now, let's go to the next hard part. We have 2 solution methods. Actually, I'm going to introduce you total 4 solution methods, but the last one is not that important. First 2 are important. Number 1, critical value method. Number 2, probability value method. Now, before starting these, let me give you a fair warning. Both are important on their own. Both are significant. Now, do you have to learn both? The answer is probably not. If you go to our textbook, according to our textbook's problem, you have to know both. It gives you problems in both ways. And a little bit more emphasis is in solution 2, probability value method. But I'll design a course in such a way, at least in my exam, I'll design it in such a way that if you know one method thoroughly and if you just use it, you're going to be okay. I cannot say the same to MyMathLab, okay? So if you're doing MyMathLab and you are asked to do something different, then that's what it is. That's what MyMathLab is. In my test and in my homeworks and my quizzes, I'll make sure that if you know one method and do it, then you can get full credit. Now, which method? Critical value method, in my opinion, is easier for you, and historically, students scored better this way. I've been teaching statistics for actually quite a long time. The first time I taught statistics, elementary statistics in university level was the year 2001. So what? It's over 20 years I've been teaching this and tried many things. And then over the years, I found that students for doing this usually scored better. Our textbook, by the way, emphasized this one more, and my personal favorite is again solution 2. I like this one better, probability value method better. Why? This one has a sounder theoretical foundation associated to this type 1 error and type 2 error business. This. So if you understand this and the conditional probability, type 1 error, type 2 error, alpha and beta, those kind of things very, very well, then you'll probably like the probability value approach better. And that's usually the case for all the professional mathematicians, and they are the ones writing the textbooks. So they naturally emphasize the probability value method more. So if you go through some lesson videos made by MyMathLab or WebAssign or MathXL or whatever, usually the emphasis is in solution 2. But I found through my experience that students usually score better through solution 1. So I'm going to emphasize solution 1 more. And I was very verbose in all the explanation here on the background, but I'm not going to repeat it anymore. I'll just give one video on critical value method and one video in probability value method, and then label those, and then you just follow accordingly. In this video, I'm using critical value method. Okay, all right, let's begin. Here's the setup. Yes, we went through that. And then here's a picture associated to the critical value method. Outline and the center, which is the null, and then the end is the critical value. This x value is the one you want. And then there's 2% of chance that goes the other way, consequently 98% of chance in blue region. That's because the problem gave you the alpha value as 0.02, which means if the null is right, if you have expected value indeed 75 minutes, then the sample mean will fall in this blue region with 95% of chance. 98% of the time, the sample mean will fall in the blue region. And the other 2% is going to fall here simply by luck. And 2% by luck, I'll assume that's low enough. So if my sample mean falls into the red region, I'll say it's too far away from the null, and then go with alternative. If it falls in the blue region, then close enough to the null, so null wins. And threshold is the critical value x1. All right? So I'm looking for this x1 value. How do I do that? Well, the same deal all the time. The z-score is end minus center over SE. Z-score is, let me make this font bigger, end minus center over SC. That's the z-score here. And x minus mu 0 over sigma over square root of n, that's my z-score. And that has to be associated to 2% there. So what is the z-score associated to 2% to the left-hand side shading? Look up the z-table and get it. I'll leave that to your own exercise. After all, by now, everybody should have mastered the use of z-curve. So we have negative 2.05. That'll allow me to calculate all that, and I got 71.31 as my threshold. 71.31, and that gives me the final picture. 72.3 fell in the null region, close to the null, so null wins. We reject the alternative and accept the null hypothesis. Does it make sense? This is a threshold. Close to the null, then null wins. Far away from the null, then null loses. That is the critical value method. We just went through that.